Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at how we can use all of the various intermolecular forces to help describe the properties of all the various states of matter. So when we're looking at various phase properties, we can generally divide them as being caused by one of two key features, either cohesive forces, and so these are going to be the forces that where IMFs hold a substance together, so how much a substance likes itself. And in general, the stronger the IMFs, the more stable the condensed phase will be. So if I've got very strong IMFs, I'm going to tend to want to make a solid. Weaker IMFs, a liquid. Very weak IMFs, gases. However, this isn't the only way that IMFs play a role in condensed phase properties. Another key one is going to be adhesive forces. So this is how well a substance can form intermolecular forces to a different substance. So when we're thinking about this, think about it as it will adhere to a thing like an adhesive, such as tape. So tape has very strong adhesive forces. Substances like water also tend to, cling to the walls of building. It has good adhesive forces. It likes other things. And this is a very kind of good way to try and look at the world. So we're going to go ahead and start by talking about cohesive forces, as they are play a much more critical role in describing systems. So if I'm going to go ahead and look at, say, a solid, one of the things that tend to make solids literally solid is the fact that they tend to form very rigid structures of intermolecular forces. So they tend to like things where you've got either small molecules with strong IMFs, like hydrogen bonds in the case of water, or maybe lots of weaker IMFs, such as fats. But one of the big things is that they tend to form these very consistent lattice-like structures, which we'll talk a lot more about later. But what ends up happening is if I add a little bit of energy to the system, well, then these molecules will start rotating around and moving about. And then this lattice starts to break down and it becomes liquid. And that's really one of the big things we're looking at with the importance of cohesive forces, is how rigid the structure is and how likely will it make an ever-moving mass. And so to a certain extent, what we're looking at is the resistance of those forces to the movement of temperature. And so as a result, one of the biggest things that we're looking at IMFs is phase stability. In general, if I have a stronger set of IMFs, I'm going to tend to make a higher freezing or melting point. It will take more temperature to break those bonds because I have to break all of those cohesive forces. It's going to be easier to break a weak dipole bond than it is to break a hydrogen-hydrogen bond. And it's going to be very hard, going to take a lot of temperature until I can, break an ionic bond. You often need to get to thousands of kelvins to break ionic bonds because they are quite stable. Similarly, a substance, if it's got strong IMFs, it's also going to resist moving into the gas phase. So it'll tend to have higher boiling points, because this is going to be the temperature which all of your IMFs break down, because there is no IMFs in space. Gas phase molecules, no IMFs. So what we're often looking for is you can most reliably determine the strength of cohesive forces by looking at the boiling point. And as a result, one of the things we can do is look at the cohesive forces in a liquid by using several observable properties, the biggest of which is going to be vapor pressure. So this is literally, if I have a liquid, how much of that liquid is leaving into the gas phase? Because one of the big things to make note of is anytime you have a liquid, some small portion of molecules will end up leaving the liquid and seeing what's out there. And so what you can do is look at the partial pressure of that substance above the liquid. So for example, if I've got water, there's always going to be some water vapor in the air. If I've got a cleaner like Windex, there's always going to, which contains a lot of ammonia, there's always going to be some ammonia in the air. And so the vapor pressure is going to be the partial pressure of that gas above the surface of that liquid, again, if I give it enough time to come to equilibrium. So essentially, Think about sealing that pot off, not letting all that water vapor just expand until it reaches a happy point. And this will be the vapor pressure. And we're going to be talking about that a lot more next time. And so this is found in a number of substances like acetone. Generally, if you want to think about a system's vapor pressure, a good general rule is if you can smell it, it's in the air. Because in order to smell something, there has to be some molecules that are wandering around in the air. So this even applies to if you can smell iron. It means there's some iron in the air. So most things will have a vapor pressure, though for many substances, it tends to be quite low. And we'll be talking about this much more in the next lecture. But there's a lot of forces that we don't always think about quite so much. So another great example of a cohesive force is surface tension. So this is the amount of forces required to break the plane of a liquid. So if I have something like water, water has a very high surface tension. And this is because water has good hydrogen bonds, strong cohesive forces. And so many insects and some lizards can walk on water, because what ends up happening is as they put force down on the water pushes back because it doesn't want to let go of its connections to other molecules. Another major feature of surface tension is you can often throw small objects like leaves or paper clips on water, and they exert so little force that the water would much rather stay together than to let something heavier fall through it. So that surface tension is resisting gravity. It's also the surface tension that makes water droplets. It makes rain look like rain because this water wants to hang out with itself. It does not want to go into the air. It likes itself too much. And this is at its heart a cohesive force. The final major cohesive force we're going to be talking about is viscosity. So this is going to be very related to the surface tension. And this is really just the resistance of a fluid to flow. So if I pour a liquid, if it likes itself, if it has high cohesive forces, it's not going to want to move. It wants to stay together in one mass. It almost starts acting like a solid if the viscosity is high enough. And this high viscosity is the origin of slow as molasses. Molasses does not like to flow. It acts rather like honey, which has a fairly high viscosity. There's lots of other substances where as you strengthen the cohesive forces, it starts acting like pastes, chocolate syrup, ketchup, toothpaste. I mean, it does flow, but not well. This high viscosity is the origin of the fact that when you pour ketchup, it either comes out in one glop or not at all. It's because it doesn't want to break apart. It wants to stay together. Now, on the other end, if you have something very low viscosity, so this would be things like good motor oils, which will make things flow and move over each other very nicely, well, it works pretty well. Acetone has such a low viscosity that if you go into the lab and you pick up one of the acetone bottles, which we use as cleaner, because of its low polarity, it will actually leak out of the top as soon as you grab the container. It wants to flow that much. And so these are various ways that we can use how much a substance likes itself to predict its general behaviors. And vice versa. If you have a high viscosity substance, you know that it has very strong IMFs. Now, one of the features of a liquid that we don't often think about quite as much is adhesive forces. So how much a substance wants to hang out to other substances. So one of the classic examples is water. Water, being very polar, tends to like ionic substances and very polar substances a lot. And one of the classic examples is that if I put water in glass, which has silicates, it starts to flow upwards. And so if you look at a water in a glass container, it forms that meniscus that we often talk about in the lab. And the reason why is because water is polar and silicate is an ionic substance. So glass is made up of an ionic material. So the water says, ooh, I want to hang out with those ions so hard. And so it starts creeping up. But because it's also has a fairly high surface tension, it does want to stay together. And so as a result, this is the origin of the capillary action of the meniscus, is it's due to this capillary action where it wants to flow up a highly charged surface. And so it is worth noting that if you tried to do the same thing with acetone, acetone doesn't interact with silica enough to generate the same sort of forces. So this is very particular to water. And one of the very cool things is you'll notice as you raise the ratio of silicate to water, that capillary action starts overcoming both the viscosity and the surface tension, and you can watch water increasingly flow upwards. And it turns out plants make use of cellulose and other materials to really amp this property up in the steroids. And as a result, this is how water flows up into the leaves of plants. As plants can encourage this capillary action to keep the water moving and keep their leaves nice and moist. Now, as a good general overview, looking at these properties for various materials. If I've got a gas, there's almost no IMFs present, and as a result, and the substances are quite spread apart, so it's quite compressible, it's easy to move, and easy to pour into another substance. And again, very low viscosity because there's no cohesive forces countering it. Liquids, fairly good IMFs, not great, not as compressible because it has some movement, but not a lot of room for flexibility. But because of those ever-changing networks of IMFs, it can move into different volumes into different containers, as long as you don't essentially try and compress it too much and you're not running into issues of surface tension. And again, moderate viscosities. Solids, however, have infinitely high viscosities, as only very select kinds of solids can actually flow. And they're quite rigid against any sort of change. And all of this is due to those incredibly strong IMFs. So next time, we're going to be looking at the role IMFs play in the phase change going from liquids to gases as we dive in much greater detail to vapor pressure. Until then, take care.